Let's consider this signal here. So for t less than 0, the value of the signal is 0, and for t greater than or equal to 0, its value is 1. Now this signal is called unit step, and this is a continuous time unit step signal. Now this signal suddenly changes from 0 to 1 at t equal to 0. Now if you observe the signal at t equal to 0, we can see that there is a discontinuity at t equal to 0, because the signal changes from 0 to 1 instantaneously at t equal to 0. Now this signal could represent a switch on of a DC source. So this is a really useful signal, and by giving this as input to the system, we may get an idea about how the system responds to sudden changes in input. Now let's see the formal definition of unit step. Now the unit step is mathematically defined as u of t equal to 1 for t greater than or equal to 0. That means when t is greater than or equal to 0, its value is 1, and for t less than 0, its value is 0. Some textbook, specifically in textbook by Oppenheim, have seen that it's defined slightly differently. That is, u of t is 1 for t greater than 0 and is 0 for t less than 0, which leaves the signal undefined at t equal to 0. But in most of the textbooks, I have seen this definition of unit step signal. That is, its value is 1 for t greater than 0 and at t equal to 0 also. This definition is followed by Mr. Simon Heikin also. So you do not need to worry about this. Now we can use this signal to create many different signals. Let's see some popular examples. Let's see how u of t minus 5 will look like. U of t minus 5 means the signal should shift right by 5. This is our reference line, that is t equal to 0. Now this was our original u of t. Now it's shifted right by 5. That is u of t minus 5. This is our u of t minus 5. Let's plot u of t plus 5. That means u of t should shift left by 5. This was our original u of t. Now we have to shift it left by 5. Now this is our u of t plus 5. That is u of t shifted left by 5. Now let's see them side by side. This is u of t. This is u of t minus 5. This is u of t plus 5. Now we will see how we can form this signal here using unit step signals. So this signal, its value is 1 from minus 5 to plus 5, and it's 0 elsewhere. So if you recall, this was our u of t plus 5, and this was our u of t minus 5. So we can form this signal by subtracting u of t minus 5 from u of t plus 5. Let's say this is our new signal x of t. So this is u of t plus 5 minus u of t minus 5. Let's see them side by side so it will be more clear. So this is our u of t plus 5. This is u of t minus 5. And by subtracting u of t minus 5 from u of t plus 5, we will get this signal, that is x of t. Now let's consider another case. Let's say y of t is equal to u of t plus 5 into u of t minus 5. Now what will be the plot of y of t? So we are taking the product of u of t plus 5 and u of t minus 5. So from minus infinity to minus 5, its value will be 0. That's obvious, because u of t plus 5 is 0 and u of t minus 5 is 0 in that range. 0 into 0 will get 0. That's correct. Now here, from minus 5 to plus 5, u of t plus 5 is 1, but at the same time u of t minus 5 is 0. So in that range, we will have 1 into 0. That will be 0. So it has to be 0 here. So let's plot y of t. Now from minus 5 onwards, the value of u of t plus 5 is 1, and here also its value is 1. So we will get 1. So this is the plot of y of t, which is u of t plus 5 into u of t minus 5. So we can use unit step to truncate the signal in the desired area. Hope that you have understood why it's called unit step. because there is a step and the value of that step is 1. So it's called a unit step signal.